because this is going to be like a very technical deep dive thing, so I hope you got your coffee. A couple of years ago, 2018, I was at JFall, and I was talking about qubits, quantum computing, like all the amazing cool things you can do maybe 10 years in the future. And that was cool and all, but we don't have to forget the normal bits, like the ones that make up my laptop and this beamer and this air conditioning unit. Everything, your phone, everything is working because bits have these amazing properties. And in this presentation, I want to showcase some of these properties and basically nerd out over some random stuff. So what are we going to talk about? What is binary? How do we store numbers in bits, especially floating point numbers? How do you store a floating point number in bits? Does anyone know it? Why don't we know that? That leads us into a very cool trick that was used in Quake 3, which is called the magic inverse square root. And I'm going to explain how it works and how you can derive that solution that they came up with. Then we're going to create any program on Earth using just booleans. And lastly, we're going to solve all the problems in the world using bits. So it might be a little bit ambitious, but I think we'll be able to manage. So George Boole, old dude, lived like 150 years ago. He was sick and tired of math and algebra and all these weird large numbers, and he said, well, can we just use 0 and 1 to describe everything? Turns out he was right. We can use zeros and ones in algebra and derive all these cool things. So let's start with a quick refresher. We count in base 10. Why? Because we have 10 digits. Like, that's how we evolved to count. So we go from 0 to 9, and then we put a 1 in front, and then we continue. Same thing in binary, but just 2. So you start with 0, 1, and then you have to put a 1 in front. So this is what we end up with. This is how we store regular integers in binary. So at the moment we run out of a 0 and a 1, then we're done. Then we need to put a 1 in front, and we can continue. So in Java, we have the following numbers. We have, well, you don't really have a bit, but they do exist. But we talk about bytes, which is 8 of them. Shorts, 16 of them. Ints has 32. Longs, even double. It's 64 bits. And that's the way we store numbers. But it's just positive numbers. How do you describe a -1 in binary? Also, gates. The NOT gate, very simple. If you have a 0, you do NOT, you get a 1. I'm using the Java notation with the tilde. The AND, 0, 0, 1, 0, 1, 0, 1 is all 0. Only if they're both true, you get a 1. And an OR is if either of them or both of them is true, you get a 1. So if we have this big number, how can we use this in Java to see the actual bits? It turns out you can call a two-binary string, and then you get the bit representation as a string. You can just look up the numbers. How it's actually stored. It removes all the leading zeros because most of the time you don't need them, but this is an int, so it has 32 bits, and it's stored as 4 separate bytes. But the first byte is a special byte. This is the sign byte. All the others are used for the number, so you have 31 bits for a number. The first one says if a number is negative or positive. If you have a 1, all zeros, that's the lowest negative number you can have. So the 1 means it's a negative number, all zeros is the lowest negative number. Then you start with 1 and 2, and you start to add numbers until everything is a 1. That's -1. And if you add 1 more, it automatically overflows into 0. And then you continue counting, etc., until you're at this number. And then there's 1 more, and that's max value. And if you add 1 more, you might have seen that, this becomes a 1, this becomes all zeros. So if you go from max value +1, you get min value. But yeah, that's just how it works. That's how overflows work. Like I said, that's an overflow. So when I started programming in 2004, 2005, I was doing a Java ME gaming. I worked at a Java ME gaming company. So we wrote mobile phone games in the time when you had Nokias, etc. Those were very, 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 very slow, and we wanted to do Java on it, so that made it even more slow, and we had to do all kinds of weird tricks, like every time we had a division by 2, we weren't allowed to do a division by 2, we needed to shift the number, because shift is more efficient, and it's the same thing as dividing by 2. So if you have a number, you shift it one place, then it's the same as dividing. If you shift it the other way, it's the same as multiplying. Yes? Is that still the case today, or does the JVM revert to shifting? This, yeah, but right now the compilers are so efficient that they will just mitigate that. Especially runtime optimizations will completely eliminate that. Yeah, in those days it was very important for us that we did that. We also had like crazy tricks where we had a game sprite, but we couldn't store like multiple images, so we had one image and like a small lookup table which had the colors, and we can just change the colors inside this lookup table to actually change the picture. And for example, so we had like a team selection where you had a shirt, but you could use a slider to pick a color, which was for that time amazing that you could optimize, could personalize your character, but we couldn't store like 10 images for 10 different colors. That was way too big. So, something about shifts. If we have this number 16, there's just a single bit. If we shift it to the, for you, right, that's the same as dividing by 2, so this is 8. And you can see that we're actually shifting in a 0 there. If we shift 2 places the other way, it becomes 64. Yeah, very good. And you can see we're shifting in zeros from that side. There's this weird thing. What happens if you have this min value and we shift it one place to the right? What happens? If you shift normally, it will keep the sign. So in this case, it will have the same sign as you had before. So it's still a negative number, but a larger negative number, a much larger negative number. If you use the triple shift, then you always shift in a 0. So there are 2 different shifts. You don't have it the other way around, just that way. There are two options. You can either use the normal shift, and that uses the same as the sign. If this was a 0, it gets a 0, and if this is a 1, it gets a 1. And if you use this one, you will get a 0, always. Now you know. Some cool things we can do, masking. For example, if we have this number, and somebody told you, I hid a secret message in there, and it's actually the part in orange. That's the secret message. How do we get this secret message out? Well, we can shift it. Like we said, we shift it 2 bytes. Then we have this. And this is a mask. So we make some place, we make all ones. And if we AND those things together, we get like the thing we want to have. So to get the orange part, we can just shift, but to get just the blue part, we can use a mask to get that part. Yeah, it's the same in Java code. This is how you can use a mask. So you just make some bits 1, and you AND them together, and you only get the ones that you made 1, because that's how AND works. The one we didn't show yet is the exclusive OR. It's just like OR, but more exclusive. Normally in an OR, this will be 1, but in an exclusive OR, we just want one of them to be a 1. If they're both 1, then it's a 0. So how can we use this? We've all done this. You have 2 numbers, and you need to swap them. What do we do? Well, we make a temporary variable, then we assign y to x, which is now overwritten, and then we say temp is now y, and we've swapped them. Did you know you could also do this? No temporary variable. but we still swap the values around. So how does this work? Suppose we have a certain value x, which is the value 1, and we have a second value y, which is value 2. If you take the exclusive OR, you kind of get the difference between the two. So right now, if we do this, we get x holds the difference between the two values. If we now have y is y and the difference, which means you get v1 back, like the original x. And if you do it a second time with x, which is still the difference, and you do it with y, then you get v2 back. So without using any variables, you can do this, and this is just a little bit faster, actually. So these are kind of tricks that we used in 2005. Famous example, floating points. So now we've seen like normal integers, we see how it works, but why does this happen, Java? Why? Why is it not just 0.8? It would be so much easier if it was, but it's not. This is a float in Java, and it's actually made out of 3 parts. There's still the sign bit, which is the same. We've got this exponent. This is a number between -128 and 127. And we have the mantissa, which is 23 bytes. So how can you calculate what it is? Well, it's actually -1 times the sign. It's just a minus or a plus. Then it's 2 to the power of exponent. And then the mantissa is 1 and something. Really crazy. So let's go through an example. You get these bytes. You get these bits. What number is this? Well, we can decode this. There's a 0, so we know it's a positive number. Then we have this number. It's 2 to the power something, and this something is a number between -127 and 128. So in this case, the number 1000111 is 135. If we subtract 127, it's 8. So it's actually 2 to the power 8. And then we have this mantissa bit thing, and it's always, this turns out to be always a number between 1 and 2. So we always start with 1. This is like, you can forget it. And then the first bit is 2 to the power -1, 2 to the power -2, 2 to the power -3. And given if this bit is 1 or 0, we actually use it. So if you would calculate this, or same thing, so 1, if it's true, you add a half, we add a quarter, we add an eighth, we don't add a 16th. That's what we do. So we end up with this number for the mantissa. This is the exponent. So the bits you actually saw here was the number 492.6. Sure. We've seen the integer to binary string to get the bits. Did you know you could do get float in int bits? So this actually takes the floating point number, which is 492, and you get the bits as if it was an int. So it doesn't just like remove this and give you the integer 492. No, it gives you these bits. And using that, we can do cool stuff. First, let's try it the other way around. What if we have a certain floating point number and we want to get to the bits? Well, we need 0 because, again, it's a positive number. We can see that this number we have is between 128 and 56. So it's between 2 to the power 7 and 2 to the power 8. So we take 2 to the power 7. We add 127, so we have to encode 134. That's the exponent. And what is this magic number? We need to multiply it. So we need 2 to the power 7 times this number, the mantissa, to get the floating point number we want. So we need to encode this mantissa. How do we do that? Oh, we again check. Is it larger than a half? Then yes, we subtract it and we write down a 1. Is it larger than a quarter? No, it's the leftover is not larger than a quarter, so we write down a 0. It's not larger than an 8, so we again write down a 0. And it's it is larger than a 16th. So we write down a 1. And we continue until we have all the bits. And this is what we end up with. Sure. And if we would take that bit string, we again do the float to int bits, do the int bits to float, so it's the other way around. We take the actual bits and we turn it into a floating point number. You can actually see that we're off by a little bit. Like, there's not enough room in bits to describe the 1, 2, 3, 4, 5. So there's already a rounding error here. But you can see, even if we would have taken this number and we didn't do it by hand, but we used the computer, we get the same bits out of it. Like, that's the best thing we can do. By the way, did you know you can do this? Like 0B and then have a binary number. And then you can use underscores in a number to denote like a space, which just gets removed. This is valid Java. And not a lot of people I know knew this. Now we get to one of the coolest uses of this. And this is actually from Quake 3. And not so long ago, a couple of years ago, the source code was released. And people started digging around in the source code. And they found this little method. And the comments are actually from Quake 3 itself. So there's evil floating point, bit level hacking, what the fuck. First iteration, second iteration, this can be removed. So let's see, wait. Let's first translate it to Java, because we are Java programmers. Let's see what's happening here. So this is a function that does the inverse square root. And why does it do an inverse square root in Quake? Turns out, if you want to do 3D graphics, you have a lot of triangulations, and you need to do a lot of inverse square roots to basically display everything. And in Quake, performance was like a big thing. It was revolutionary at the time, and it had graphics nobody had ever seen. So they needed to do a lot of new, cool, innovative tricks, and this is one of them. So a float goes in, and the inverse square root of the float goes out. So what they do first is they take this floating point number, and they say, well, just give me the bits as an integer. That's already strange. Magic. And then they turn it back into a float. What happened there? This part is actually a well-known algorithm that is, what is it called again? You can basically, it's a zero finding function that you can keep calling, and every time you call it, it better approximates the zero. Turns out they needed to do only one iteration. The other one was there. They tested with it, but they decided to comment it out. If you would add it like 5 more times, the answer would be even better. So I want to focus on this thing. I want to understand where this number comes from and what it actually does. So let's say we have this floating point number, 16. 16 as a floating point number is this. And I'm going to show you why. Oh, I'm not going to show you why. What we want to end up with is 1 over the square root of 16, which is a quarter. So we want to go from the top one to the bottom one. How do we do that? Well, the top one means it's this number minus 127 is 4. And the mantissa is all zeros, so that makes it 16. It's 2 to the power 4 times 1 is 16. So we've concluded that this is indeed the floating point bits of 16. If we have some exponent and we divide it by 2, if you divide an exponent, that's the same as taking a square root. So that might come in handy. So if we would do 2 to the power 2 instead of 4, then we get 4, which is indeed the square root of 16. That's nice. That's nice to have. And we don't want the square root, we want the inverse square root. And how do you do that? Turns out you can just negate it. That's cool. So if we do, instead of to the power 2, we do minus 2, we get a quarter, which is the inverse square root of 16. So here's a crazy idea. What if we have this number, we shift it 23 places. So it's just 131. Then we subtract 127 to get the exponent 4. We divide it because we want to divide the number by 2 to take the square root. Then we inverse it, so we multiply it by -1. Then we add back the 127 because we want to turn it into a float again, and we shift it all the way back. And then we get the quarter that we actually want. So this is like a step-by-step how we could do the inverse square root. This is probably faster than calling mat.inverse square root. Basically, this is what we're doing. So there's just a single calculation we do to calculate this inverse square root. We learned something more. We learned that shifting 23 places, that's the same as dividing by 2 to the power 23, or that big number there. If we would replace the shifting by this is just a mathematical expression. And I'm going to spare you the math, but this is something we can simplify. And if we simplify it, this is actually what you end up with. It's the same calculation as before. Now, if we take this number, we multiply it out, and turn it into hex. And instead of doing divide by 2, we shift one place. That looks vaguely familiar. We've seen that before. If we will put it in our magic formula, so we've just created this. And that's it. It's basically just shifting, subtracting 127, adding it back again, and all that stuff, but just in a single calculation. Yeah, well, you have to subtract and do one shift, but that's it. And if we take some random numbers and we call our new function, the q inverse square root, and we would calculate the actual inverse square root, you can see that the error is always less than a tenth of a percentage, or maybe 0.2. It's always less than 0.2. And for a game like Quake, perfect. Very fast, no issues. Maybe if you zoom in really close and you stand in the corner and things go like this, nobody noticed. There's blood everywhere, so. Awesome. Okay. So that was just warming up. Now we've become familiar with bits and we've seen some cool things. Now we're going to step it up and maybe a little bit more ambitious. We want to create any program on Earth using just booleans. Let's start very simple. There's a small, this is a program, takes 2 input bits and has 1 output bit. And I call this program 1. In this case, very simple, the output just zeros, like very simple. Turns out if you list all of them, all the unique 2-bit numbers with 1 output, there are 16 of them. Makes sense, right? And if you look closely, some of them might look familiar, like this is bit A and bit 2, 0001. So we can write that one down. That's the OR, also very simple. This is just B, so forget A, just return B. Some of them are a little bit more difficult. For example, program 5 is 0100. How would you write this? What we can do is if we have not A, 1100. And then we have B, which is 0101. And then we can AND those two things together like a mask. And then we end up with 0100. So program 5, also solved. How about program 10? This is the most complicated one. We want to have 1001. Well, first we AND both of them together to get a 1. Then we do the same thing as above, but we also negate B to get the top bit. And then we OR those two things together. So this one is pretty long. We use some operations, but we can actually make this program work. Turns out we can make all of them work. Like I said, P7 and P10, they are a little bit bigger. Some are very, very small. Like, for example, there's A and B and not A and not B. But all in all, we can make any 2-bit input, 1-bit output program. But Roy, that's not enough. What if we have 2 bits as output? Well, that's actually very simple. If you have 2 bits of output, Well, the first bit, that's program 5, and the second bit's program 7. So just do them. So we can have any amount of output bits, right? We can just run some programs, and then we get any output. But Roy, what if we want to have a 3-bit program with multiple inputs? Turns out that this is also relatively simple, because it's just two 2-bit programs. This was some program, this was another program. And there's this bit in front, which is 0001111. Masking. We know how to do this. So if we have not A and the first program, and we have A and the second program, slap that together with an OR, and we got the output that we want. So using this rule, we can take all these 16-bit programs and combine them to make any program on Earth. So if you want to replace my entire MacBook, just describe every input bit and every output bit, I can give you the program. So a 4-bit prime searching program. So takes 4 bits, 15 numbers, 16 numbers as input, and it returns true if it's a prime number. Well, same trick. We take these 4 programs, we look up their logic gate configuration, we combine the first 2, we combine the second 2, and then we combine those 2 results together using these bits, and we're done. And if we want to have multiple outputs, we just run multiple programs. So using Boolean logic, you can create any program on Earth. This is completely Turing complete, like everything. And to see if it works, I actually copy-pasted this entire thing. I'm running over the numbers from 0 to 16. I'm extracting these bits. How do we do that? Well, we shift and we end with a 1 to get that bit itself. And sadly, it's Java, so it doesn't automatically turn true into a 1. Then we run our isPrime program that we just programmed, and then we print the output, and you can see that for all the prime numbers, it returns true, and for other numbers, it returns false. Applause. It's magical. But there's one gate, like we've been using NOR gates and OR gates and AND gates, exclusive OR, but this is NAND, and it's not AND. And this gate is magical. It's special. It's more special than any other gate. For example, if we have this NOT gate, which just flips a bit, we can do the same thing with a NAND gate. A NAND A just flips a bit because it's not AND. So we can eliminate the NOT gate. But the AND gate, well, this is not AND, so it already does AND. And we know how to do a NOT. If you do A NAND B, it's the same thing as an AND, but inversed. And if we want to inverse that back, we just NAND it with itself. So A NAND B NAND A NAND B is the same as AND. We can eliminate that gate. But what about the OR? Well, you can see this already looks really close, like it's the same thing, just flipped upside down. If we do A NAND A to flip A, B NAND B to flip B, and we have A NAND A NAND B NAND B, we do the same thing as an OR gate. So we can eliminate that one. Wait a minute. We've eliminated them all, which means there's actually not one king to rule them all. There's a king and a queen. There's also the NOR. They're both universal gates. These gates can replace all the other gates. They can do the same operations as a NOT, an AND, and an OR, and an exclusive OR. So using just NAND gates or just NOR gates, you can build any program or any computer on Earth. So now you might be wondering, is that how computers work? Is everything just NAND gates? Kind of, but also not really. Like we do a lot of stuff more often than others, like adding 2 numbers together. So it's very convenient to have an adder, which just takes 2 binary, 32-bit numbers and adds them together, or 264 and add them together. So your machine and your computer is much more optimized than just NAND and NOR gates, but it doesn't have to be. NOR gates brought us to the moon, because the guidance computer used on the Apollo mission was using just NOR gates. This is what it looked like. I wouldn't want to touch that thing. But their idea was really simple. If we want to go to the moon, we want to make this completely fail-safe. We want to make the components that we are using like perfect. So they perfected that thing. Why would you want to perfect 3 different gates if you can really perfect one of them? So they decided, let's make one incredibly secure, very good NOR gate, and just use that one, instead of using all different kind of gates. And you could actually swap things out, because everything is just a NOR gate. So, really smart move. And now on to the final challenge. We've shown already that using bits and bytes and booleans, we can basically create any program. But did you know you can also solve all the problems in the world? And to do this, we're going to dive into Boolean satisfiability. Who here has used a set solver before? Nice. Didn't. Oh, more people than I figured. Most of the time when I talk about set solvers, people say, no idea what it is. So the idea is, if you have some Boolean expression, is there a set of assignments? So you give a variable 1 or 0 that makes the entire statement true. Let's look at an example. This thing, can we make this true if we set A and B? Well, no. But luckily, the computer knows. Actually, yeah, we can. There are multiple solutions here, but if we have A is true, B is false, C is false, and D is true, this entire thing is true. That's the whole concept of a set solver. So you have some statement, can we make this thing true? How can we use this? First, some terminology. This entire thing consists of a lot of variables. We know variables, we're programmers. If you say something is A, we know that if A is true, that means that that thing is also true. It's the same thing, it's a name for something. That's a variable. If we use a variable at a specific spot, we call that a literal. So this is a literal, this is literal B, this is the literal negative B, that's one literal. This expression is in a very specific, written down in a very specific way, which means that all the literals here are grouped by OR. And if we do that, we call that a clause. And this clause needs to be true, and in the end, all the clauses are combined with AND. If you rewrite your Boolean expression in this way, it's called the conjunctive normal form. And it turns out any Boolean expression can be written down in the conjunctive normal form. Maybe you've learned at school that if you have like an OR operation, you can actually negate it and use an AND to get the same thing. Like you can manipulate any Boolean expression to be in this specific form. We're programmers, we love file formats. We have like JSON, XML, sadly we also have YAML. There's also a file format for this, and it's called DMAX. So how do you write DMAX? I'm actually going to teach you something today. First thing is, instead of AND, we just new line it. Second thing is, now every clause is on a new line, so we can remove the brackets. And there's one little weird thing in the DMAX file format. Instead of negative, we use a negative sign. And instead of actually using variables, we use numbers. So in this case, A becomes 1, and C becomes 3, and basically everything turns into a number. Finally, we can remove the OR, because, yeah, it's already there. And now we're done. Like, this is the DMAX file format. And there's actually a 0 on the end, no idea why, because there's already a new line. And there's a small header. And this small header says P, CNF, and then the amount of variables and the amount of clauses. So, quick test. How many variables does our program have? 4, yeah. And how many clauses do we have? Yeah, 3 lines. So now we've created our first set solver input problem. And the weird thing is, this is enough to take a generic solver online and actually solve this equation. So if we write this to a file, I did that, example.sat, then I run some set solver I downloaded, in this case miniset, and I call it with example.sat, and it writes to an output.txt. And you see that it does a lot of things. So again, we see that the number of variables is 4, clause is 3, it has some statistics, and it does stuff like a restart, it detects conflicts and decisions, but in the end, the only thing we're interested in, it says this problem statement is satisfiable. It means that the thing we inputted at top, there is a valid solution in binary. And if we output it, this is one of the valid solutions. So if we put the first variable a as false, the second, the third, and the fourth as c, b, and d as true, we get true. So this gave us one answer. What if we want to find all the different answers? And after that, I'm going to tell you why you would need that. So this was our original program, and we have one solution. If you want to find the next valid solution, you just take the solution we have, and you add it to the input, but you flip everything. So that means we add a new class to our program, which means A is true, B, C, and D are false, and one of these things needs to be true, which means that the solution we had is now no longer valid in this program because one of these, of the original, now needs to be the inverse of what it already was. So that means if you run it again, and again, and again, and again, and you keep adding the negative of the result you got, we actually end up with 1, 2, 3, 4, 5, 6 different solutions to our problem. If you want to get solutions back, just invert these, and then you get all the different solutions. That's a bit weird. It doesn't automatically do that. I don't think it would be very hard to actually implement it, that it automatically does, but that's just how set solvers work. Most of the time, people are interested in just a single solution, not all the solutions, but there's a way to get all of them. Nice, cool. How is this useful? Let's go through an actual useful example. So what if we have this Sudoku and we want to solve it using just booleans? We can. It's actually, on one hand, it's not that complicated. On the other hand, we're going to need a lot of booleans. But luckily, we're programmers, so we know how to work around that. We can just write a program that outputs all the booleans for us. And that's what we're going to do. Short recap. How does the Sudoku work? You have this problem, and each cell can contain exactly one number. Important, you cannot write multiple numbers in a single cell, obviously. Each row contains every number once. Each column contains every number once. And each 3x3 block contains every number once, like these nine different blocks. And that's it, that's the rules. How on earth would you take something like this and turn it into booleans? Let's start with the first rule. The first rule is each cell contains exactly one number. So we're going to focus just on this first one, this first little cell. And we create 9 different booleans. So we have, I'm going to label them anyway, so I'm not going to use the numbers. I'm going to use labels in this case, just to make it a little bit easier to understand. You can always turn that back into a number. The first cell can be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we write down this rule. One of these things needs to be true, or more things need to be true. So now we know that at least one of them is true. And now we say 1 and 2, one of these needs to be false. 1 and 3, one of these needs to be false. And you continue for every combination. And if you do that, we've now guaranteed that one of them is true, but not 2. Any combination of them, they're not both true. which automatically means that for each cell, only one can be true. That's how you kind of describe the problem for an SAT solver.
So you're back to zeros and ones.
Everything's zeros and ones, yep. So in Dmux, it would look something like this. How do we do it for a row? Well, the logic is kind of the same, but yeah. So for row 1, column 1, value 1, for row 1, column 2, value 1, for row 1, column 3, value 1. So in one of these, there needs to be a 1. There also needs to be a 2 in one of these. There also needs to be a 3. There also needs to be etc. And then we're done. Like, if there's a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, and a 9, there cannot be 2 2s, or one and another one somewhere else, because there are no more holes. We have already said that each cell can have only one number, and now we've encoded that every row has to have every number. For a column, same thing. For the block, also, same thing. So we just encode that for each of these 3 by 3 cells, there's all the numbers in there. I wrote a small Java program to actually output the numbers. They get really big because you start with, how much is Sudoku? It's a 9 by 9. So it's 9 times 9 times 9 different variables, and we need to describe rules about all these variables. And what we've now ended up with is a generic Sudoku solver. It can solve any Sudoku. But we want, if we run the program, we get a valid Sudoku solution, but we don't want a valid Sudoku solution, we want this valid Sudoku solution. So the only thing we need to say is row 1, column 1, value 5, and that one needs to be true, because we want that one to be true. Row 1, column 2, value 3, we want that one to be true as well. So this way we fill in all the numbers, and this is what we end up with. In total, there are 729 variables, so 9 by 9 by 9, and there are 3,240 different lines, different clauses. And if we run this in the set solver, this is what you end up with. It finds a solution where all these 729 variables mean something. And actually, let's look at the first 9. So this is negative, 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 positive, negative, 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 negative. So for the first cell, we see that only 5 is true. And this is true for all variables. So we can actually take this output. Let's make it a little bit more readable. And then you can deduct this. We've solved the Sudoku. This is applause, yay. This is So if you are able to describe your program as an SAT program, you can just throw it in a generic solver. I wrote my own solver. Like, these solvers are actually very simple. Like, the simplest way to make a solver is just, if we make the first thing true, do we have any conflicts? If not, then we take the second variable, we set it to true, and then we continue, and then you can just backtrack if you have some conflict. If something says, well, now we can never be true in the entire statement, then you go back. So as long as you are able to describe your program, and basically any program can be described as an SAT problem, then you can just give it in a very advanced like neural network solver, and it will give you the correct answer, which is really powerful. And I've actually used this in competitive programming to solve problems, which is very cool. Was always like, I wanted to understand how it worked, and now I do. Because set solvers like, if there was a problem, I'll solve it, like any problem. And now we're out of time. I wanted to talk about POSIX. POSIX is a different way to store floating point numbers. And it turns out for neural networks, you can actually get a speed up of like 50% if you store your floating point numbers in a different way. Because for neural networks, big, large floating point numbers, not that interesting. Like small floating point numbers around 1, very interesting. So there's a different way to actually store these numbers. Turns out also you can do the tangent function very fast on posits, which is something that happens a lot in neural networks. So we might be transitioning to a different kind of floating point number. So how does this set solver work? I like described how mine worked in a dumb way, but there are like, I built one that actually learns new rules. So you start the set solver, it runs into a conflict, and from that conflict it can generate new rules and actually use them to solve your problem faster, which is very cool, but a little bit too advanced for today. Also, these set solvers are incredibly efficient because even if there's like a long list of things ORed together, it just looked at 2 of them. Because one of these needs to be false, and it can just very quickly do a hash lookup and check which ones are actually watched, and the other ones not that interesting. So there are a lot of cool optimizations you can do in building an SCT solver. They often have restarts. Why does that happen? And yeah, like I said, some of them can learn new rules, which is very cool. But yeah, that's all for another day. So I want to thank you for your time. We're out of time. So.